Hello, welcome to lecture 3. Today, we are going to talk about programmable data planes. Before we talk about programmable data planes, let's do a quick recap of what we learned in lecture 2. So in the last lecture, we talked about how software-defined networking extracts simplicity with better abstractions. More precisely, it talks about 3 different abstractions. One was distributed state, the other was specification, and third was forwarding abstraction. SDN realizes these abstractions with different instantiations. For distributed state, the idea is to develop a network operating system. An example is ONNX that some of you have already read. Specification can be realized with network virtualization. An example is FlowWiser, and forwarding abstraction can be realized using programmable data planes. And an example is Open Virtual Switch. In today's lecture, we will be focusing more on programmable data planes. So the learning objectives for today's lecture are that we will be talking about what type of different data planes do exist. They can be implemented in software, they can be implemented in hardware. What is the difference between the ones that within the hardware, but they have fixed function forwarding pipeline, or the ones that have the deconfigurable or programmable forwarding pipeline? And what are the limitations of fixed function forwarding pipelines? And then what is this concept of protocol independent switch architecture, and what new functionalities do they offer? So as we learned in the last lecture, that software-defined networking is all about separating controls and data planes. So when host A and host B were trying to communicate in a traditional network, then the intermediate routers had both data plane and control plane juxtaposed with each other. In software-defined networking, the idea is to take away the control from these individual devices, or that is disaggregate the control and data plane and provide the abstraction of a network operating system. So software-defined networking is all about separation of the control and the data planes. So far, when we look at this example, we have always considered hardware switches, right? So we have always considered the data planes to be implemented in hardware. But when we talk about the host, and especially talk about the host from the data center networking perspective, then each of these hosts will also be hosting multiple virtual machines, right? And these virtual machines will also require communication with each other. So this type of communication can be enabled with a virtual switch, right? So virtual switches were developed to enable communication between all the different virtual machines that exist within these physical servers. But technically, when we talk about software-defined networking, these virtual switches can also be controlled using the network operating system. So in a nutshell, data planes that can be controlled by the network operating system can be implemented in both software and hardware. And in today's lecture, we will be covering both these type of data planes and try to understand what are the differences between the two. So we will first start with a software virtual switch. And more specifically, we will be focusing on Open Virtual Switch and OVS. So an OVS, as we discussed earlier, is enabling packet forwarding between different virtual machines that reside on a physical server, right? And this OVS can be programmed using OpenFlow. So now you must be wondering, what is the genesis of this Open vSwitch, right? Or Open Virtual Switch? So Open Virtual Switch was designed to enable flexible control for different VMs that not only sit within a physical server, but also within a data center context that sits across multiple physical servers, right? And those physical servers can be within the same data center, or they might be communicating over public internet across 2 different data centers. So let's consider an example where we have these 2 physical servers. Each of them have these different VMs, and the color of the VM here is indicating that a VM of color yellow belongs to the same organization. The VM of color green belongs to a different, and the blue belongs to a different organization, right? And there will be instances when the yellow VMs might want to communicate with each other, and the physical servers might be located at different locations such that this communication might require sending their packet through the public internet, right? So in this context, because the network operating system can be used to program the packet forwarding logic at the virtual switches as well, so this entire control of the packet flow between different VMs across different locations can actually be completely done in a software, right? So the program or the logic can be that if the destination is remote, then encapsulate the packet using IP signal. And the IPsec can be used to add the tunnel header, and then the traffic can easily use the public internet to go from one VM to the other without requiring any type of special changes to the networking configuration of the IP addresses for these VMs, right? So in general, the Open vSwitch were very, very useful for simplifying the management of virtual machines, especially in context of multiple or multi-tenant data centers, right? And this was basically the genesis of the Open vSwitch. These were developed internally for network control platforms that were developed by a startup called Nicira, which was eventually acquired by VMware. And this was developed internally for that company, and then it was upstream with Linux. And then it got a lot more usage beyond the NCP platform, and it is widely used, or it was basically very, very critical in making OpenFlow as well as software-defined networking more robust and mainstream. So before I talk more about this, I just want to make sure that like Open vSwitch was very, very critical, and it enabled a lot of network virtualization abstractions as well. And this is something that we will cover next week, right? So we will be revisiting Open Virtual Switch when we are talking about network virtualization next week. So now you might be wondering, what is Open Virtual Switch, right? So in a nutshell, it is a multi-layered software switch. It is a production quality implementation in C, and it is publicly available under Apache 2 license. And it supports multiple virtualization technologies like Xen, KVM, VirtualBox, etc. So what are the key components of Open Virtual Switch? One key component is this module that is implemented in kernel, and that is responsible for handling the packets coming through the network interface card, right? So the servers have a physical network interface card, and those are handled by the module that is implemented in the kernel. And then like this kernel basically provides the connectivity to the virtual network interfaces that are enabled for different VMs on the physical server. This kernel module, because it is implemented in kernel, so it has or it offers limited functionalities, but it is relatively speaking, it is very fast because it can handle or it can process a particular packet in less than 1 microsecond, right? But because it offers limited functionalities, then the other functionalities are enabled via a module that is implemented in the user space. It is called OVS vSwitchD, or the virtual switch daemon. And this is the one which basically performs multiple tasks, like, it interfaces with different types of other modules as well. The other one such module is the OVS DB server, which basically maintains the state for different type of operations on the switch. The OVS switchd also talks to the network operating system using OpenFlow. So now let's try to understand these components in a bit more detail. So the kernel module, which is called openvswitch_mod.ko, which is not a very funny or fancy name to have, but like .ko basically represents that it is a kernel module. It performs it executes the match action operations that are enabled or that are required by the OpenFlow, right? So when a packet comes in, it tries to match on the header fields or a combination of header fields to find a flow ID or a rule ID. And then depending on the match that we have in the data plane or in the kernel cached for that rule ID, it applies that action, right? And whenever it cannot find a rule, then it sends that packet to the user space for processing. It is ironically agnostic to OpenFlow. The way this kernel module is implemented is not specific to OpenFlow. So that, like, in any other day, if you want to change OpenFlow with something else, we don't really need to change this kernel module. What we really need to change or like update is the implementation of the user space. And it offers an interface called OVS DPCTL. So OVS DPCTL is the one that is used to interact with this kernel module. The other module is the virtual switch D, or virtual switch daemon. This is, as I mentioned earlier, that this is the one that communicates with different modules. So this is kind of like the heart of this system. It interacts with the kernel module over the netlink, and then it interacts with the remote network operating system using OpenFlow. And then it also interacts with OVS DB server using a management protocol. It also performs some other operations, like, it implements the packet mirroring, like port bonding, and virtual LANs using OpenFlow. And it checks the data path counters to handle flow expiration and start requests, right? So something to note here that the implementation kernel module does not keep track of things like flow expiration and other stat requests. So this is something which the implementation, the user space is responsible for, and then it updates the entries in the kernel module using the netlink. It offers different interfaces for the programmers to interact with the system. Most notable is the OVS OpenFlow CTL or OFCTL. Open vSwitch also offers an very interesting database called OVS DB Server. This database holds switch level configurations. The log-based database here offers some nice properties. Like more specifically or more interestingly, it offers these value constraints, like something about the weak references, and it also supports garbage collections. The interface that it supports, I think I have that wrong. It supports some other interface. I think like I need to fix this problem. I will correct that in the slides when I send that to you. So far we were talking about the virtual switches, but the OpenFlow, as we know, also controls or can program the hardware switches. So now we will talk about the hardware switches. And before we dig into the details of different types of hardware switches, a typical bare metal switch, what are the like key components of a typical bare metal switch? One will be all these ports that are that offer different connectivity speeds. 40G is an example here, but you can have port speed up to 100 gig. And then these ports basically interact with network processing unit, which is responsible for handling the packets. And the key component within the forwarding pipeline, like within the network processing unit, is the forwarding pipeline. But in addition to the forwarding pipeline, we have some SRAM, which is used to buffer the packets. And then there is a CPU level control as well. And then the CPU of the switch basically interacts using PCIe Express to manage the network processing unit, right? So one thing to note here that there has been an evolution or a journey that I briefly mentioned in lecture 2 as well, that the switches before software-defined networking came into the forefront were mixing both the control and the data plane in one switch. So they were very bulky and expensive and power hungry. So they had more CPU attached with it because they were also performing all the control plane operations. But now when we talk about the switches, which are bare metal switches, these are now dumb devices. So the CPU part of it has shrunk significantly, and more resources are spent on the ASIC part, which is responsible for handling the packets, right? So another thing to note here is that because the functionalities that are required, are not very proprietary. So one can use merchant silicon to implement the bare metal switch, which has significantly reduced the cost of these switches. For reference, I think a powerful switch that can handle traffic up to the workload of a couple of terabits per second would have cost of the order of few $100,000 in the past, but now we can purchase that in less than $10,000. So I mentioned a forwarding pipeline here, and the pipeline that typically most of these switches offer is called fixed function forwarding pipeline. Let's try to understand why it is fixed function forwarding pipeline. So the pipeline, when the packet comes in, has a parser, right? Because the packets from different protocols are coming in. So we need to implement a parser that tries to understand, okay, what is this? What is the content of this parser before we can make any decisions, right? So once the parsing has been completed, the parsing can help us identify what are the layer 2 or the Ethernet header fields, what are the layer 3, which is the IPv4 header fields or IPv6 header fields, and then maybe some layer 4 header fields as well, which might require extracting out the TCP portions of the packet as well. The head, like we call this fixed function because the order in which some of these tables can be applied are fixed, right? So what do I mean by table? A table can be a layer 2 table, which is matching on the, say, destination MAC address and then deciding where to forward this traffic. or it can be matching on the IPv4 table, that is the, say, destination IP address, and then decide what will be the next hop IP address. Or it, like, similarly for the IPv6, and the ACL tables are the ones that are used for implementing functionalities such as firewalls, right? So it can be matching on a combination of source and a destination IP address, or maybe a TCP port as well, to decide whether that traffic or that packet needs to be dropped or not, right? So whenever you buy a switch for a fixed function of switches which have the fixed function forwarding pipeline, everything is pre-decided and compiled or like minted in the ASIC, right? So how, like, in what order these tables will be applied is fixed, and what will be the sizes of each of those tables will also be fixed, right? So how much memory will be used to implement an L2 table, and how much memory will be used to implement an IPv4 table. These are all fixed when you buy this switch, right? So this is something which was a limitation even when we had OpenFlow, because with OpenFlow, you were able to configure that, okay, how are you going to, or what fields are you going to match on? But the sequence in which these tables were implemented was already fixed when you buy the switch, right? So that was a lack of flexibility that was out there. And we'll, as we will proceed further, we will try to understand what are the limitations, or like why these fixed function forwarding pipelines are limiting from software-defined networking perspective. Another thing to note here is that we read about the Open vSwitch, and that is something which is completely implemented in software, and it will definitely offer, it does offer a lot more flexibility than the fixed functions, right? Like there is no limitation on how many L2 tables you will have or how many L3 tables you can have. And there is definitely no limit on the number of entries that you can have in layer 2 or number of entries that you can have in layer 3, right? So that is where you're using CPU for performing switching operations, right? But the conventional wisdom in 2010 was that the programmable switches, the ones that are as flexible as the CPU switches, consume more power and they cost a lot more, right? This is something which was conventional knowledge. And this is because, when we're talking about programmable switches, we're talking about all the flexible, like C-like programs that can be written as Open vSwitch. All the functionality that we can think of can be offered when we talk about programmable switches, and expectedly that is actually slower, or will be slower if you're trying to implement those functionalities in an ASIC, right? So this is a result from an experiment where we are trying to evaluate, or evaluate how many packets can be processed by, in terms of, or like at what rate that packets can be processed. The metric on the y-axis here is gigabits per second, and this is the workload for one chip, right? So when we talk of a hardware implementation on a switch chip, then we can think about this number to go up as high as 10,000 Gbps, right? So 10,000 Gbps is around 10 Tbps, right? So it's a bit less than that. Around 6.4 Tbps is what was promised around in 2015, 2016. But compared to that, if you're using a CPU based switch, then this was always slow, but the gap has kept on increasing as we improved the switch technology. So in around 2015, 2016, when these ideas of programmable switches were coming up, this gap was around 80 times, right? So it is clear that you cannot use CPU switches for packet forwarding, but the programmability or the flexibility that we need in handling these packets is still a desirable goal, right? And if we look at the trends, all domains have a domain-specific processors, right? So when we talk about general purpose computing, then we have CPUs. When we talk about graphics, then we have GPUs. When we talk about signal processing, then we have these DSP chips. And when we talk about machine learning, then we have TPUs, right? So the question has always been that what is a domain-specific processor for networking? And the answer that was explored as it came out around 2014, 15, or maybe earlier time frame was called PISA or RMT, right? So PISA here stands for Protocol Independent Switch Architecture. And the other name for it is called RMT, which means reconfigurable match action tables, right? So we will learn about why we call them protocol independent switch architecture, or why we call them reconfigurable match action tables. But the idea here is that this was a burning question for the networking community that every domain have their domain specific processors. What is the domain specific processor for networking? The fixed function forwarding pipelines that we had in the previous generation of the switches were not really the answers because they offer limited flexibility. That's why the networking community was looking for something which was more programmable, more reconfigurable, right? So another way of looking at this problem is that the switches were designed bottom up. That is, the fixed function switches already had those tables and layouts already in place that like you can read in the switch specification, and they would that like those specifications were telling you that okay, this is how I process the packet, right? And then that information is something that is conveyed to the switch operating system, and then that's how the programmable devices or the control programs were operating, knowing that okay, these are the limitations, these are the constraints under which we have to work, right? But the networking community started questioning that, do we really have to follow this bottom-up approach? Can we come up with a top-down design instead, where we can specify that, okay, this is precisely how you must be processing the packets, rather than the switch actually telling us that how it's going to process the packets, we program that how the switch should be processing the packet, right? So we can define custom headers that it should be parsing, and the custom set of operations that it should be performing in the packets, and that specification goes down, and then this new configuration for the switch comes out, which we can use for our use cases, right? So that is what, or that is why this PISA-based switches were designed, or the protocol switch architecture was designed. And now we will try to understand the nuances of those PISA-based switches and try to see how they address the challenges that were faced by the SDN community when they were trying to use the fixed function switching pipelines. So what is a protocol independent switch architecture? Unlike the fixed function pipelines, when we talk about a PISA switch, when the packet comes in, first we have a programmable parser, right? So a programmable parser enables us to support any new header fields, right? So we like because this parsing logic is not fixed, so we don't have to decide ahead of time that what type of protocol are we going to use, or what type of protocols can a particular switch handle. If tomorrow I come up with a new protocol, then I can actually program this parser such that it can handle or it can parse the packets for a new protocol that I come up with. And then I don't have to buy a new switch to support that, right? And so that is one functionality. And this is the key reason why, the name for this type of architecture is protocol independent, that I don't have to sign up for the protocol that a particular switch can support when I buy the switch, right? And this is something very important to understand and appreciate, that before this type of switch architecture came out, if you are going out in the market to buy a switch, you have to be very careful about what type of protocols do you really require to support in your network, and the switch that you're buying is actually supporting it or not, right? And this is a one-time decision that you have to make. And this is something which is very, very limiting from the innovation perspective, that if you come out, or if like a researcher comes out and say like, hey, I have a new protocol that will make your network efficient and that will help you save $500,000, right? But then because I've already signed up, or maybe I've already spent tens of millions of dollars buying these devices for a different protocol, then I will not be able to leverage this new protocol, right? And that type of approach, or that type of limitation, stagnates the progress significantly. Another point to note here is that even if I come up with a new protocol and everybody is convinced that this new protocol is very, very good, but for me to go through the process where I will interact with the switch vendors such that they can understand what this new protocol is, and they can include that in the new version or the new generation of switches that are going to come out, all this process takes a long time, right? So this is not a software process, right? So this is where the community was conflicted when they were talking about software-defined networking, but they were severely limited in terms of programmability that existed in the data plane itself, right? So this is the key motivation or reason why a protocol-independent switch architecture was designed, right? And the protocols is not just the only thing, it's also about how the packet is processed, right? So in a PISA switch, we have a fixed number of stages. All these stages are identical, right? And all these stages support match action tables that can be programmed over time, right? So like what is like another way of looking at it is that these pizza switches, you can think of them as, like blank chips that when you buy them, these are just blank chips, right? And then after buying, you can decide what type of operations you want to perform with these switches. And then you can program individual elements that you have in these switches so that they can perform those desired operations, right? So I can, allocate certain amount of memory for an IPv4 table, certain amount of memory for IP v6 tables, and then like for L2 tables, and then decide whatever order I want to apply them, right? So this is the flexibility that I get, and because the match action tables here are reconfigurable, that is why the another name for this architecture is also called RMT, or reconfigurable match action tables, right? So this is how, at a high level, the pizza switch architecture looks like. A packet comes in, you have a programmable parsers. The programmer declares which headers are recognized, which headers are not recognized. And then we have the sequence of match action tables. Here, the programmer declares what tables are needed and how packets will be processed. Notice, as I mentioned earlier, that all stages are identical, which means that they have the same amount of memory and ALU in each stage. And when the packet goes through all these stages, at the end, we have a deparser, which will serialize the packet back such that we can send out a legal packet out of the switch. So now let's try to understand how a particular packet is handled here. When a packet is coming in, it will have different header fields, right? So depending on how you have defined the programmable parser, it will extract those header fields, right? And technically what it does is that it creates a packet header vector, right? So in that packet header vector, different fields can go in different parts of the header vector, right? And then this header vector goes through these identical stages, which are each configured independently. So now, depending on how these stages are configured, different fields will go through different transformations, right? And after all these transformations are applied, then these transformed fields will be packed back into or serialized back into the packet's header, and then the legal packet will go out, right? So now, as I said, that these individual stages can be programmed independently. So I can configure this pipeline such that the first stage will perform or will implement an Ethernet MAC address table. The second, the first half of the second table can implement an MPLS tag table, where it is looking for the MPLS tags and then like applying or attaching those tags on the packets. And then the third and fourth stages can be used for an IPv4 or implementing an IPv4 address table, right? So recall that in network routing, this is typically the job of a particular router where you are matching, you're doing a longest prefix matches on the destination IP addresses, and then deciding what is the next hop to which I should be sending the packet, right? So I can typically, if this is at the internet scale, then you'll require around 1 million entries for IPv4 address tables, and you might require multiple stages to implement that, right? But here is a lot of flexibility, right? So I can implement some ACL rules in the second stage, or I can, divide resources between the IPv4 address tables and the address like IPv6 address tables. I have all kinds of flexibilities. I can also change the order in which I implement these tables, right? So let's try to understand the flexibilities that are offered by the PISA architecture using example. And something that I missed to point out earlier, that the language that we use to program these PISA architecture or PISA switches is called P4, right? So now we will use that example and we will refer to this P4 language to understand how PISA switches are enabling a flexible packet processing pipeline, right? So before we dig in, let's try to understand that what we are trying to implement is a control program where we are first matching on the Ethernet field, and then we are matching on a table which is implementing your new encapsulation protocol that you have developed, right? And then we are matching on the IPv4 and IPv6, and then finally implementing or applying the ACL. So like the parsing function or the parser will look something like this, that your encapsulation layer is sitting between IPv4 and the Ethernet, right? So whenever the parsing tree looks something like this, that if it's an Ethernet and then type matches to the encapsulation type of yours, then it will first parse the your my in-cap thing, and then it will start reading the IPv4 fields, right? So, and then like, there are three options that it has. It from Ethernet, it can go either to parse the my in-cap, or it can directly parse the IPv4 if there is no encapsulation, or it can, depending on whether it's an IPv4 or IPv6, it can try to match on the IPv6. And then all of this will lead to extracting the TCP header fields, which might be useful when we're trying to implement the ACL, right? Because when we're trying to implement ACL, then we might be matching on the port TCP ports or the UDP ports. Oh, I'm sorry, not the UDP ports. The TCP ports might be used in ACL. But this is a simplification. Technically, you can have like you can also have a parser which is also extracting the UDP fields, and you can have ACL entries that are matching on UDP ports as well. So, as we were talking about earlier, that the first layer in the packet is the Ethernet. So Ethernet, and the header type is Ethernet. Then the parser is specifying that, okay, I need to read the Ethernet header type. I have destination address, I have source address, each of them are 48 bits. Then I have this field called ether type, which is 16 bits. And this basically tells us that, okay, what type of Ethernet header is this? And then we have another custom header type, which is your custom my in-cap T. And then you can define different fields that exist in that encapsulation layer, foo, bar, blah, blah, blah. And then like, what is the next protocol that to read after that? So when we are implementing this parser, the parser will say like, okay, extract the Ethernet layer first. And then depending on the ether type field, the value of the ether type field, it can decide whether it needs to read the my in-cap field, or it needs to read IPv4, or it needs to read IPv6, right? So moving on, now we talked about the parser so far. Let's talk about what goes after that. Now we have different types of tables that we can implement. So a table is basically a match action table. So it is going to perform a read operation, and then it will have an action field, right? So in this case, an IPv4 LPM table can be implemented by reading the IPv4 dot destination address and performing a longest prefix matching operation on that. And then the action can be to, there can be two actions depending on how the match goes. It can be an action to set the next hop, or it can be an action to drop the packet, right? Expanding on this action type of set next hop, the action can be to modify a field. Say, for example, the second line here talks about modifying the egress port, which is the port that the packet will take going out of the switch, right? And then it can also update the TTL value for the IPv4. So overall, I think because if you want to implement this control pipeline, or the sequence in which these tables have to be applied, because we have the layer 2, the Ethernet table applied first. So the ingress part, when the packet comes in, it will apply them in sequence. That, okay, first it will apply L2, then it will apply your custom table, which is matching on some foo bar fields that you have created. It can match on that, and then it can put a condition there saying like, okay, if it is a valid IPv4 packet, then apply the IPv4 table. If it isn't, otherwise apply the IPv6 LPM table, right? And finally, after all these operations, apply the ACL. So this is how you can actually flexibly program. And I can change this, and I can actually say that, okay, maybe I want to apply the ACL before I apply the IPv4 tables, right? So there is complete flexibility in how I can express this control program for the P4 switch. And before talking about how programmability is used, let me go one step back and try to help you understand the value of this, right? So imagine a world where this type of flexibility was not possible, right? So if I am in a data center, and then the rate at which the innovation happens in data center, especially because you control all the devices in that network, is very, very high, right? And this was such a stifling thing that was going on in the networking community, that we had all the flexibility in terms of the algorithmic development or progress that we were able to make, but because these hardware data planes were not as flexible, that's why we were stuck adopting or using some old protocols or old algorithms for optimizations. But now with this P4 switch, there has been a tremendous adoption going on in the industry, especially in the data center networks, where these data planes can be reconfigured. There was also a cost argument here, right? And something which I briefly covered earlier, that whenever a new protocol, new algorithm comes in, you don't have to throw away all the older switches that you have bought. You can actually reconfigure them using the P4 programming languages. And that is something which has been a huge draw for this type of architecture as well. And in fact, one of the marketing tagline for these architecture supporting switches was that you only buy a switch once, right? So their argument was that, it doesn't matter how your protocols and algorithms are going to evolve. All you need to do is just reconfigure your switch such that you can support those new protocols, and you don't have to, give away your switches over time. And like from industrial perspective, this is something very important point to understand and appreciate, that phasing out older switches was a very, very common practice. And this was, as you can imagine, something from operational perspective was something very, very expensive as well, right? So the argument, it might sound a bit cheesy that you only have to buy switches once, but it was very, very powerful and effective, right? Especially think about the data center networks that are going to buy switches in the order of hundreds of thousands. For them, saving this much of money and being not able to forced to replace the older switches is something which is a very, very appealing argument, right? Okay, so these are the arguments that I wanted to make, that, okay, we have this fixed function, we had this fixed function switch pipelines. Those were very fast, right? Compared to CPU, those are very, very fast. CPU-based switches, or the virtual switches that we were discussing earlier, they were very flexible, right? You can do whatever you want in whatever sequence you want, whatever new header fields, whatever you come up with. Everything was very, very easy because it was all implemented in software, right? The fixed function switches, they were very good in terms of processing, right? Because with the switch CPUs or the virtual switches or the CPU-based switches, the challenge was scale, right? It's very flexible, but you cannot go beyond a particular rate, right? So you are going to spend around a microsecond processing the traffic, and you might not be able to go beyond, say, 80 times 6.4 Gbps, right? So a few hundreds of Gbps, or even 100 Gbps is actually like too much of a goal for the CPU switches. When you try to achieve a 100 Gbps goal on a CPU switch, you are basically significantly limiting the amount of flexibility that you want to support, right? So the point that I'm trying to make here is that when we talk about software switches, they're very good if you want a lot of flexibility, but you don't have a scale challenge, right? And when we talked about the fixed function switches, they were very, very good in terms of scale, but they offered very limited flexibility. And PISA switches was something which is trying to bridge the gap between flexibility and scalability, right? So these PISA switches are something which offer you a lot of programmability, but still those programmability is limited by, there is an abstraction provided that, okay, the programmability is there to change the amount of resources that you're allocating for different types of control programs. But it's not a general purpose computer, right? So some of those general purpose computing support is stripped away, and that has enabled you to provide limited but useful flexibility, but it is scalable, right? So the packets, like any program that can be compiled on a PISA-based target, ensure that it can be processed in the order of few nanoseconds, right? Which is very, very different from what you can do with a CPU-based switch, right? So whenever we talk about a CPU-based switch, we're talking about a delay of around a microsecond. But whenever we are talking about a switch implemented in the hardware, especially the PISA switch, we're talking about a delay of around a nanosecond, right? And whenever it's around nanosecond, it is also called as line rate. So line rate processing. Okay, so moving on. The programmability that I was talking about is very useful from cost perspective. It is very useful from flexibility perspective there, but there is a lot more value that this programmability is offering, right? So one such value is that it is capable of reducing complexity, right? So now when you have certain set of tasks in your mind that, okay, these are the set of tasks that my switch should do, you can write a program switch.p4, and then the compiler will push the program down, right? So earlier when you were buying a switch and then you you're basically taking a superset of all functionalities that you might need in the future, right? And that is just bloating in all the complexities into the switch, right? So what I'm showing you here is basically all possible operations that a particular switch might need to perform. But if I'm using switch for a particular use case, I might not use or require all of them for a particular switch, right? For an individual switch. So I can write a different switch.p4 and get rid of whatever I don't need right now and just compile the program or just compile the switch that provides me the functionality that I need for a particular use case, right? So this is how the complexity can be reduced when we talk about this top-down approach rather than a bottom-up approach. Moving on, the programmability that is offered by these piece of switches also enables adding new features, right? So we already discussed this example where we can add a custom encapsulation layer. We can add a custom table which matches on this encapsulation layer. So this is a one abstract example of how that can be used. This is very different from, or this has kind of like changed the way the network protocols can evolve. The protocol complexity for 20 years has been that you had Ethernet layer, then you had IPv4, IPv6, or whatever IPX. But now, when we talk about the data center networks, there has been a huge amount of innovation that has happened, and the amount of protocols or the amount of customized layers that you need to support has grown significantly. And it is almost impossible to build a switch that can support all possible requirements that you will have in a particular switch for say next 5 years, 10 years, right? So that is something which is very, very, very hard, especially in context of data center networks where the pace of innovation has been very, very fast, right? So there are a lot of examples that I can cite which talk about the new features that can be a requirement and can be supported with PISA-based switches. So one example is that if you want to add a new encapsulation layer, if you want to enable some new type of tunneling, or you come up with a new way in which you want to tag packets for some type of special treatment, or if you come up with some new approaches for routing. For example, you want to enable source routing in data center networks, right? So maybe some of you might be wondering what is source routing. So in source routing, rather than matching on the destination, you match on the source to figure out like where this traffic has to go, right? So this is one example of source routing. Or in some sense, like other way of looking at it is that at the source, the path that the packet has to take is already encoded in the packet, right? So that is an example of source routing, that the decisions are kind of like already made at the source itself, and then the network has to just implement those decisions as the packet goes through. The another example can be that if you want to come up with some new approaches for implementing congestion control, and one such example has been that if you want to perform some of the control operations in the data plane itself to expedite how fast you can make those decisions. Those decisions or those new features can be supported if you have a programmable data plane in place, right? And again, it also offers new ways to process packets. And another very, very important use case for these programmable data plane targets is network telemetry, right? And this is something which we will revisit later in this course as well. But what I want to cover today is how network telemetry gets enabled, or how these programmable targets are actually enabling network telemetry that was unimaginable before, right? So what is fundamentally new now? So consider the setup where you have these two set of data centers. You have a network that is connecting, like one rack with the other. So you have packets going from, host A to host B, and then there are a bunch of questions that I might be interested in if I want to, provide a in-depth telemetry here. So the three questions can be that which path did my packet take, right? So what was the path that my packet take? This can be answered by if the switch somehow had this information, so like, okay, I visited switch 1 at this time, and this time is actually recorded the granularity of some nanosecond, and then I visited switch 9 at this time, and then switch 12 at this time, right? So this is something which is giving me a very in-depth understanding of the path that my packet took. And this is something which is logged at the granularity of the packet level, right? The second very critical question, if I can answer, will be very helpful, is that which rules did my packet follow, right? So a packet is taking a particular path because it is following certain set of rules, right? So an example here can be that, okay, there is a rule ID 75 on the first switch, and then that is the one that this packet has like matched on to make this decision, right? So if the packet was also telling me that, on when I went to switch one, I saw this rule 75, and then I used that to get to the next hop, right? And when I went to switch 9, then I saw that there was a rule ID 3 which was matching on the head on my headers, and then I went to the next switch, right? So if I have this much information, that is very, very useful from like debugging what's going on in the network, right? And the third thing is that how long did my packet queue at each of those individual switches, right? So if I want to understand, or diagnose the performance of a particular application or a flow in a particular network, then this question is also very, very handy, right? And the question can be that, okay, like on the first switch, I had a delay of 100 nanoseconds. On the second switch, I had a delay of 200 nanoseconds. But on the third switch, I actually had a huge delay, which was around 19 milliseconds, right? So now this is good enough for me to know that, okay, this packet was having issues, and it was having issue at the third switch, right? And I can see that, okay, there is a significant increase in the queue size at this switch as well. So now the next question, if I can answer, will help me debug this problem, is that who did my packet share this queue with, right? So what were the other flows that were present in the same queue at the time when my packet was there, right? And this is something which is possible if I have the similar set of insights from the other packets, and I can actually correlate the two numbers to figure out what's going on. And I can see, okay, like, there is this orange color flow, which is actually contributing a lot to the queue size at this third router, right? And that's how I know that there is an aggressor flow that is sending all the packets to the switch here, and that is contributing to an increased queue size at this switch, and which is contributing to a huge delay here as well, right? So these are the bunch of questions that if I can answer, I can actually debug a wide range of performance problems in the network, right? So let's try to recall what those 4 questions are. Which path did my packet take? Which rules did my packet follow? And how long did it queue at each switch? And who did it share queues with, right? So these are 4 fundamental questions, very critical. And what's very interesting and important is that a programmable device can potentially answer all these 4 questions at line rate, right? And when I say line rate, which means that it does not require any additional CPU level processing, this can all be answered by, like information that can be extracted from the network devices itself without requiring any, like operation which uses CPU or flexible CPU. So let's try to understand how that can work or how this in-band network telemetry can work, right? And it is called in-band because all this telemetry operation or data collection is happening within the network or within the hardware data plane itself, right? So there is no software involved here for data collection, not data analysis, right? So when a packet comes in at the first hop, it will collect the information that what is the switch ID, at what time did I arrive here, what is the delay in the queue, and which rules did I match on, right? So if this is a meta information that I can collect from the switch and add to the packet itself, right? So the packet can carry this information, and the next hop when it goes, it adds the same set of information. Then on the third hop, it adds a similar set of information. And then finally, before the packet is leaving the network, I have these 3 set of meta information collected on the packet. I will send this meta information to a collector where this can actually be stored as a data base or data store and then analyzed and maybe replayed to do performance diagnosis. Right. So notice that I'm stripping away all this meta information when the packet is leaving the network because I don't really want hosts to make any changes here, right? So there is no implementation or no changes that are required at the host level. All these operations are happening at the network itself, right? And this type of functionality or feature, it's called in-band network telemetry or INT, right? And this is something I believe is one of the game changer use case for programmable switches, apart from all the other arguments that I was making earlier about the flexibility, about the cost, about the complexity. But this is something which is a very, very powerful use case indeed. So overall, I would like to end this lecture with some of the key takeaways. One was that forwarding abstraction that is key for software-defined networking requires programmable data planes, right? These data planes can be implemented in software or hardware. The software data planes, such as Open vSwitch, are very, very flexible, but they are very slow, right? The hardware data planes, especially the ones which have the fixed function pipeline, they are very fast, but they're very inflexible as well, right? Inflexible in a sense that they cannot, like the order in which those tables have to be implemented is fixed. The size that is allocated to each of those tables is fixed. So this is the inflexibility that I'm talking about. PISA is very unique. It strikes a balance between flexibility and scale, right? So it is more flexible than the fixed function switches, but it is not as flexible as CPU switches, but it is definitely more than the fixed function switches, and it is faster than the software switches, right? So it kind of like offers the best of both worlds. It has flexibility, but it is limited flexible, but it is very, very scalable in the sense that it can process packets at line rate with a delay of around 2 nanoseconds, right? So with that, I will end this lecture, and I hope you enjoyed it. And if you have questions, you should consider coming to my office hours on Friday. Thank you.